Slow application response time? Is it the application or the network? In this video, I'll demonstrate one of the core use cases of the Cisco Tetration platform, Network Insights, to help IT operations answer this common question. First, I'll leverage Cisco Tetration's application dependency mapping capability to view an accurate logical diagram of the application, which will help me through a step-by-step troubleshooting methodology. Then I'll leverage flow search capabilities to quickly rule out the network and identify which endpoint of the application is causing a bottleneck and thus responsible for slow response time and ultimately a poor end user experience. Let's get started. If you're familiar with Cisco Tetration, then you already know that at its core, Cisco Tetration provides 100% visibility into every packet of every flow inside the data center through the use of a sensor framework. The sensor framework consists of various types of sensors or agents whose primary job is to collect and stream telemetry back to the analytics cluster for analysis. Now, TCP provides clues as to whether the network, application, or both are causing slow response times for the end user. One common cause of slow application response time is buffer exhaustion. This can occur when the application server is not draining the TCP socket quickly enough and can no longer store incoming packets from the client. When this occurs, perhaps because of high CPU, low memory, or too much incoming traffic, the application will send to the client a TCP window size of 0 to indicate to the client that it should no longer send data. Now, Cisco Tetration cluster analyzes the metadata of every captured TCP packet and looks for application bottlenecks. An application bottleneck occurs when there is a TCP observed window size of 0 and there are no network limiting indicators, meaning congestion flags or retransmissions. Application bottlenecks can occur in either the consumer or provider direction. Cisco Tetration exposes these bottlenecks on a per flow basis from within the UI or via the Open API. It's an easy way to quickly determine whether the application is the cause of slow response time. Let's take a look at a real-world example. In this example, a client is complaining of slow response time when accessing the OpenCart application. The network team is first to receive the complaint. Let's take a look at how Cisco Tetration can help us through these troubleshooting steps. The first step of our troubleshooting methodology is verifying the slow response time firsthand. From our client's laptop, we can confirm that there is in fact slow response time to our OpenCart application. We can also verify that response times to other websites are within the acceptable range. The network operator's next step in the troubleshooting methodology is better understanding the various tiers of the application so that we can use that knowledge within flow search to construct our search queries. To view the application tiers, I'll leverage Cisco Tetration's application dependency mapping capability, where a real-time, up-to-date logical map of the OpenCart application has already been completed and is maintained. So here is the app view of our OpenCart application inside of Cisco Tetration. Each circle represents a tier or cluster belonging to OpenCart. Each tier or cluster includes one or many endpoints. For troubleshooting purposes, we can break down this application into sections or legs to make it easier to investigate for performance. And so leg 1 consists of the path from our client to our front-end load balancer, HA proxy. Hovering over the arrow indicates that our client accesses our OpenCart on port 80 by first passing through the HA proxy tier. Leg 2 consists of the path from the HA proxy tier to the OpenCart tier. The OpenCart tier has two endpoints listening on port 80 for traffic coming from the load balancer VIP. Leg 3
is the path from OpenCart to a single shared NFS tier. Clicking on this shared NFS tier tells us that this tier lives in a different application, Pods Shared Services. And so while OpenCart has a dependency on this particular tier, this tier is not part of the owner's workspace for OpenCart. Finally, leg 4 is the path from the OpenCart tier to a single shared database HA proxy listening on port 3306. And clicking on shared database HA proxy tier shows us that this tier belongs to the same tier as shared NFS tier inside of another application called Pod Shared Services. Now that the network operator has a good understanding of how the application is mapped, the next step is to leverage Tetration's flow search capability to troubleshoot the paths for each leg of the application. So here we are within the Cisco Tetration UI looking at flow search, where we will conduct forensics on our application OpenCart for network and application performance issues. In 5 steps, we will pinpoint the exact endpoint causing slow response time to our client. As you recall from the application map, leg 1 of our troubleshooting is from client to HA proxy. So let's create a filter that searches for those exact flows. Our filter is looking for a consumer address, our client, and provider host name, our OpenCart load balancer, which is a HA proxy server listening on provider port 80. The query returns 941 flow observations in less than a second. This chart shows metrics over time. In this case, flow observations is selected for filtered flows within the selected time range. When you make selections within this chart, you will see search results for that selection, as well as the top 10 dimensions to the right that will update for that selection. You can choose from various dimensions as well. Now, what we are interested in determining is whether there is network or application latency between our client and our OpenCart application. So step 1 is to select the SRTT metric, and we are looking for any flows that show high SRTT values, which would be an indicator of network latency from the perspective of the endpoint. We see the chart is updated along with the top 10 dimensions. We also see that SRTT is low. We do the same thing for application latency. This time we see that there are flows with very high application latency values. At this point, we know that our OpenCart HA proxy load balancer is taking a long time to respond to our client. However, we don't know why. It could be that the HA proxy is causing the issue, or it could be that HA proxy is waiting for the OpenCart tier to respond, and we know that that's part of the next leg of our troubleshooting. However, this is where TCP performance metrics captured by Tetration can help. If we further filter flows by TCP bottlenecks, we can see that there are none. This means that there were no TCP retransmissions or congestion flags or problems with draining the TCP socket on the HA proxy load balancer. So at this point, step 1 is completed, and we've ruled out the path for leg 1 between our client and our HA proxy. Let's move on to step 2 and look at the path between HA proxy and our OpenCart tier. The steps are the same as for leg 1. This time we have a search query that filters flows by consumer hostname HA proxy, and provider hostname contains our OpenCart tier, listening on port 80. We look at SRTT, again, that looks fine. We can also look at estimated network latency metrics, which is different than SRTT in that it looks at latency of packets sent and received. Estimated network latency also looks fine. Once again though, application latency is high. This tells us that OpenCart is taking a long time to respond to HA proxy. Again, if we further filter flows by TCP bottlenecks, we can see that there are none. So at this point, step 2 is completed, and we've ruled out the path for leg 2. Let's move on to step 3 and the path for leg 3, which is the OpenCart tier to the shared NFS server. The steps are the same as for leg 2. This time we have a search query that filters flows by consumer hostname contains our OpenCart tier, and provider hostname is our NFS server listening on port 2049. Looking at SRTT, we see that the response times are good. The same is true for estimated network latency. When we look at application latency, this time we see that there is no issue with application latency. We can also see that there are no TCP bottlenecks. So at this point, step 3 is completed and we've ruled out the path for leg 3. Let's move on to step 4 and the path for leg 4, which is the OpenCart tier to the shared database HA proxy tier. The steps are the same as for leg 3. This time we have a search query that filters flows by consumer hostname contains our 2 OpenCart web servers. Provider hostname is equal to the shared database HA proxy load balancer listening on port 3306. If we look at SRTT, that looks good. If we look at estimated network latency, that also looks good. And if we finally look at app latency, we see that that looks fine. And so at this point, we know that the shared database HA proxy server is not slow to respond back to the OpenCart tier, either from a network or application perspective. However, when we look at TCP bottlenecks, we can clearly see that there is in fact an application performance problem in the reverse direction. What this means is that the shared database HA proxy server is indicating to both of our OpenCart web servers by advertising a TCP window size of 0 that it can no longer accept data. And so now we've validated that the OpenCart application itself is not the issue. We've determined that another application that OpenCart has a dependency to is having TCP performance issues, specifically application and not network issues. And so at this point, the OpenCart application is in the clear. And so the last and final step, step 5, is to investigate the shared services application that provides the database services to OpenCart. And so if we look at the application map of shared services, we can see that there is a path that exists between the shared database HA proxy and the shared database tier. And so we can create a search query to look for those specific flows. And so we have a query that says, look for flows with consumer hostname HA proxy, which is the HA proxy database load balancer, and a provider hostname that contains our 3 database Percona servers listening on port 3306. And if we look for any issues with network latency, we don't have any. And if we look for any issues with application latency, we also don't have any. But if we look for TCP bottlenecks, what we do see is that we do have a TCP performance issue, this time in the forward direction, which means the HA proxy server is telling the database servers that it can no longer receive any traffic by advertising a TCP window of 0. And so we've quickly determined that in fact the HA proxy shared database load balancer is responsible for our client's slow response time, and we can inform the application owner now where exactly to focus. Thanks for watching and be on the lookout for future videos.